Hello, everyone. So I'm last, I think. So I hope everyone's still awake, and there's 30 minutes-ish, and then you're free. Or there's pizza, and Axel told me he definitely didn't buy beer, which means he bought beer. I was told. That's the only reason, like someone flew in just for this. But hi, everyone. I'm Hugh Breslin. I'm one of the subject matter experts with the FPGA business unit at Microchip. And this presentation, I'm going to say it's a mental breakdown and something kind of cool all in one. So the name Zephyr squared, and the whole point behind that was 32 32-bit CPUs in one device, so 32 by 32, and it's squared. It was meant to be cool, and it got complicated. But as an introduction, that's a Guinness 0, by the way. Just it's really important for marketing point of view. But I'm Irish, so I had to get in some brand. But yeah, I'm Hugh. I'm a subject matter expert in FPGAs and SoCs with Microchip's FPGA business unit. So for anyone who didn't know, Microchip sell FPGAs. We were originally Microsemi, if you knew Microsemi, or Acto, that was us. So we've been bought over the years, and now we're part of the Microchip family. But myself, I started as a CPU designer doing 32-bit RISC-V CPUs for our FPGAs. And then I went on to do some hardware software code design in the 64-bit space when we did a 64-bit SoC. And then I learned too much, and then I became a subject matter expert, and that's it. But no, now I'm here. So as part of that move, I actually got to move to Germany. So I live in Mannheim near Karlsruhe, so it's quite cool. And I live in Mannheim because I can't pronounce Karlsruhe properly. But one interesting point to make, it's really interesting for me being here because we're a manufacturer of chips. So when anyone asks what we're doing with Zephyr, we're doing not much with Zephyr. We're enabling our customers to do their stuff with Zephyr. So it's really interesting for us to see what our customers are doing, so then we can try and make products that are better to enable our customers to do what they want. So as a quick starter offer, who here has heard of an FPGA before, not even developed? Okay, cool. That's better than I thought. Who's actually developed for an FPGA before? Okay, nice. So a few people talked about hardware design earlier, and there's obviously, does my hardware not work or does my software not work? If you have an FPGA, there's a whole new layer of, does my FPGA even work? So there's like a level of insanity that most FPGA people kind of sit on. But it's interesting that a lot of people here have used them before. So as another question, who here knows about AMP, or who has heard of asymmetric multiprocessing? Great. Okay, so for anyone who doesn't know, you're going to know by the end. And then who here has heard about RISC-V? Who here cares about RISC-V? Okay, cool. You never know, some people say no, like honestly. Okay, so as an introduction, just so we're all speaking the same language a bit. So what is an FPGA? So I tried to sum it up. I've gone through so many iterations of this slide. So it's a chip with reconfigurable hardware inside it. So we're used to getting an ASIC with a fixed function. An FPGA is like a big bucket of digital logic that you can reconfigure and stitch together. So it's loads of Boolean gates. And they're configured and wrapped together using a HDL or a hardware description language. So you type out your hardware and then program it into the FPGA, and suddenly you have this blank ASIC that's suddenly become your own custom device. And it's a bit like building software because you write HDL, like writing C, it's not the same as C. And then you run through to your logic configuration. So you kind of compile your hardware to an extent. And Microchip FPGAs, for anyone who doesn't know, they're flash-based. So that gives us some interesting advantages, like we're instant on, they're low power, and they're single event upset immune. So a lot of FPGAs can be flash-based, which means that they're RAM. And you can have a particle strike if you're in an airplane or something like that, and they can flip an AND gate to be a NAND gate. And I don't know if that controls whether the plane goes up or down. That's not really something you want to happen. So we're very good in safety-critical applications. We have a 4-element lookup table for anyone who knows their stuff. A lot of other ones are 6-element lookup tables. It gives us a benefit in terms of power consumption. And our density, like we go from, I said less than 5K gates. I didn't want to say 0, but we can go from a couple of hundred all the way up to, it's 500,000 for our largest FPGA at the moment, and going up higher. So we start at end at about 500,000 logic elements. But fundamentally, in an FPGA, like I said, you have these orange boxes are your digital logic, and they're all connected together, and these green boxes are your IOs. So you can configure your digital logic, stitch it up with other digital logic, and connect it to an I/O if you'd like to. And in some good FPGAs, you have hardened blocks, so you can have CPU on the side of that logic with some DSP in it, and then you can build all this custom stuff for your CPU. And what's interesting is Microchip, well, our FPGAs, we have a really long history of CPUs being coupled with an FPGA. So if you go back a couple of years, we have a product called SmartFusion 2, and that's an ARM Cortex M3 here, so you can do a block diagram for the SoC, and then here interfaced to an FPGA fabric. And more recently, a few years ago now, we made PolarFire SoC, so that was Linux capable, so it was 4 application cores and a monitor core with a whole load of peripherals connected up to an FPGA fabric. So, well, what does that really mean for us? Well, if we look at, and this is a block diagram from one of the AVRs from Microchip, we look at the block diagram for the ASIC. At the top, we have the CPU, and then the bus, and then all the peripherals, whether it's UARTs or SPIs or anything like that. And when it comes to our SoC FPGAs, you actually end up with a really, really similar block diagram. Because, well, there's your CPU up in the top right, and there's your peripherals around it, and then you just have this extra block here, which is basically like your unlimited peripheral. You could put anything in it. If you wanted a custom peripheral as a CNN, you could put a CNN, and if you wanted some special counter that's going to blink an LED at the perfectly specified rate you wanted, you can put it in. And the way you talk to those peripherals in your digital logic are just through these things here with the arrow pointing at them. They're called FICs, or fabric interface connections. And all that means is your accesses to your fabric peripheral, they just register reads and writes. It just becomes memory mapped. So if you make your own SPI and put it in an FPGA, you just access it at the memory mapped base address for that peripheral. So using a CPU and an FPGA isn't actually that difficult because you're just bolting your custom peripheral onto the side of a CPU at a memory mapped address. So if we follow down that plan or that point, an SoC FPGA is a CPU with a big customizable peripheral or set of peripherals. So if you need 50 PWMs, for whatever reason, you can put them in an FPGA, that's no problem. If you wanted 100 I2Cs, you can put 100 I2Cs in an FPGA, and once you have enough pins on it, that's fine. If you wanted a CNN or a neural network for drawing boxes around people's face and guessing their age from a video, we can do that. If you want to convert MIPI to Ethernet, which is actually a really good use case because MIPI has a very short cable length, so what you could do is put an FPGA on the back of the camera and then convert the MIPI interface to Ethernet and then have a whole Ethernet link running to your NVIDIA Orion in the back of your office or wherever you have it. So they're really versatile, whether it's toggling a signal at a set rate or converting from a camera interface to Ethernet, you can do it in an FPGA. And if you look at our product offering, and I'm not trying to be a sales guy for it, but more just to show the difference, with our SoC, the latest one for PolarFire SoC, you always get our processors. So you always get the monitor core and 4 application cores. And then all the FPGAs come in different densities. So they start here at 23,000 logic elements, going all the way up to 461,000 logic elements. So if you think you have 461,000 logic elements or Boolean logic gates that you can configure to build up whatever you want. And you can fit them in a whole range of different packages with different IOs. So that's what's in here. So what can you really do with the low power FPGA fabric that's sitting on the side of your setup? Well, one thing you can do is you can split a device in 2, and that's where AMP comes in. So let's say you had a PCB with processor A and a PCB with processor B, or processor B on the same one, and they're both running Zephyr. And one is, I don't know, let's say getting sensor data for your smartwatch, for example, and then another one is drawing on a display. Let's say you segregated it that way for some reason. Well, in our SoC, we have 4 processors. So we can actually split them up and then merge your CPU A and CPU B into one part together. So if we think about it, what SMP is, in a typical case, is we have an operating system, let's say Linux, and it runs across 4 CPUs. So in our case, our processors are called the U54s. We'll have our OS, on top of the U54s, and then they'll connect to memory, which is probably DDR, for example, which is where Linux is going to run from. Well, in AMP, we could also run Zephyr, for example, on one of those CPUs. But in AMP, what we do is we take a CPU from Linux, and we give it to the RTOS, and then we let Zephyr run on one of the CPUs and Linux run on the other three. So that's quite handy because we've shared memory, we've shared peripherals, we can use PMPs or physical memory protection to stop Linux overriding Zephyr's memory, so we have some security there between the two of them. But we have used a 64-bit CPU to run Zephyr and taken that away from Linux when we might not necessarily need to. So that fundamentally is AMP. And where we're going is that on the side of all of this, we still have an FPGA. So one cool thing we can do before I completely milk this to death is we can also run 4 Zephyr instances side by side. So I said originally we could have 2 CPUs, CPU A, CPU B, and then merge them all into one device. Well, we could actually do that with 4 contexts as well. It gets a bit more complicated to secure them and stop them overriding each other. But if you went from, let's say, 4 PICs on one PCB, you could merge them all into one device with an FPGA. And you could give them all their own custom peripheral set in the FPGA fabric. They can all share one memory with at least hardware protection between them to stop them overriding each other. So that's a cool feature of AMP. But it's not 32 Zephyrs in one seat or in one device. So to try and lead us down the road, and I actually had to put 2 of these slides in, I'm really, really sorry. Let's think of a problem statement. So doing a real-time task with any external components is a bit of a pain. So with PolarFire SoC, like I showed you, we can sacrifice one of our application cores to run Zephyr on it. But what if I needed more? What if I couldn't fit all of my tasks into one context running on PolarFire SoC? Or what if I wanted a bit more safety built into all of the tasks? So one example that comes up for us that's really interesting is I2C. Let's say, okay, the example I get is, let's say we have 10 sensors on I2C. Some run at a lower speed, some run at a higher speed, and some have their own, or they all have different serial addresses. And then you try to access the one that runs at the highest speed, and somehow the one that runs at the lower speed picks up some of the transactions and doesn't correctly get that it's not at the right serial address, and then you get crap on your I2C bus. So we have customers who have done something like this, where they have a microcontroller with an I2C and then a big mux on their PCB to swap between the sensors that they're accessing. And then before they access any sensor, they have to set the select bits on the mux and then hope that it's gone over. And yeah, if you've stuff in space, it's really important that the I2C definitely works if there's stuff on the end of a robot arm. So this was the best way to make it work. But there are other ways to make it happen because we're talking about FPGAs. So they're all reconfigurable. So what we could do is we can get an SoC FPGA. So let's say a SmartFusion 2 or a PolarFire SoC with either the ARM Cortex-M3 on it or the RISC-V CPUs. We can put a bus in the FPGA fabric and put a load of I2Cs on that bus, and then have an individual I2C going to each of our sensors. So now we don't have the issue of them all on the same I2C bus. They're separate. It's kind of safe. But then we have to do a whole load of work on the microcontroller or on our CPU to actually process data from those sensors. So is there a way we could make it faster and safer and better for ourselves? Well, yes, and that's the whole point of this. So if we go back to the block diagram of the AVR, this block diagram, the FPGA, is starting to look really similar to the block diagram of the AVR, just the orientation is a little bit different. So what we've actually done in the FPGA is we built our own SoC. We built a custom SoC with our own peripherals. We put them in. We've got it working in a memory map and a base address for everything. So but then it comes to, well, where does Zephyr tie into all of this? And how does it make things better? Well, the big question is what makes up a CPU at the end of the day. And it's a bit of a rhetorical question, and we're all very tired. So it's logic gates, and logic gates looking at registers and bits. So it's all digital logic. If you had an ADC on the side of your PIC, for example, it's a peripheral, it's not in CPU, you can't put an ADC in an FPGA. Or, well, It's not that easy. But you could build a CPU out of digital logic in an FPGA. And there are actually lots of them. And that's why I asked about RISC-V, because that's where it gets interesting. So running Zephyr in an FPGA. So first step is we need to get a CPU. So we actually saw this already in the first talk this afternoon. I got Neo Orbi32. It's a super easy, super small RISC-V CPU. It was made by Stefan Nolting. I think he's over in Dusseldorf. And it has Zephyr support. So I can go on GitHub and download the CPU. It's written in a hardware description language for me, so that's handy. So then I need to put it in an FPGA. So conveniently, we made a reference design for Neo Orbi32, so we can put that in the FPGA. So in a few clicks, you can get an FPGA development kit and put a Neo Orbi32 in it. And this is what it looks like. So for an FPGA, you can turn everything on and everything off, as in you can put the hardware in, you can take the hardware out. It's where it's really complicated to have CPUs because you never know what's turned on or not. But Neo is really good because it's quite configurable. So it supports a huge range of the RISC-V 32-bit instruction set. And then it also has all of these optional peripherals around it as well. So you can turn on and off having an IMEM if you want, or an iCache, or you have PWM or 16 PWM channels, or none if you want. And you can save space in your FPGA and save logic elements by turning off stuff you don't need. But when you put Neo Orbi32 in our design suite, that's what it looks like over on the right in the FPGA design canvas. It's just a whole load of pins for different peripherals and then the bus interfaces as well. What's cool is it takes up about 5,000 FPGA logic elements to run. Or to build Neo Orbi32 and have it run Zephyr. The size, like I said, varies depending on what's turned on or off. Don't need PWM, it's not there. I showed you the product table, or the density table for PolarFire SoC earlier. So it starts at 25,000 logic elements. We need 5 to run a Neo Orbi32, and it goes up to nearly 500K. So going back to what's the point? So right, I've told you all that PolarFire SoC is a 64-bit quad RISC-V SoC FPGA. And we know it can run AMP with Linux on some cores and Zephyr on others. And we know that we can put a 32-bit RISC-V CPU in the fabric. And there was some problem stuff about I2Cs. So this is where I showed you the problem statement a minute ago. So we had, let's say, Linux running up here on our SoC. We have it connected to a bus, and then a load of I2Cs in the FPGA fabric, and connected up to a load of peripherals on the other end. So Linux isn't good at real-time tasks, and we don't use it for motor control, for example. And the I2C example is one CPU managing tens of I2C devices, and it's a lot. And it becomes an issue, especially if one of those devices is inaccessible. So if one of the sensors, like one sensor goes down and then ties an I2C bus line low, then the whole bus is gone. And the real-time requirements start getting very difficult. You start running out of time because you have to read all the sensors. So, like, what's going to solve the problem or what's going to work? So in my head, my statement to that was I want Linux, and then on the side of it, I want a whole load of Arduinos. I couldn't do that. And I thought about, has anyone ever used a Raspberry Pi Pico? Yes, you have. Okay. Has anyone ever gotten one to work? Okay, no one else raised their hands if it wasn't just me. So I like the Linux and a load of Arduinos idea, and I like the Raspberry Pi Pico as an idea. I still haven't gotten it to work properly. But like, if I could do those things together, I would, and that's what we did. So what about Linux with a load of Zephyrs? So what we can do, and I didn't have space before I turned this into like a color-coded nightmare of headache for everyone. Diagrams are not my strong point. I'm not colorblind. I really don't help people who struggle with it. But what we can do is, instead of just connecting Linux directly to an I2C controller, what we could do is get a Neo Orbi32, that's 5,000 logic elements, with a built-in I2C controller that already works with Zephyr, and it already runs Zephyr, and I can connect that to my I2C sensor. And I can have my bus down here connected to some shared memory. And I can have Zephyr running and say, Zephyr, can you sit there and read the I2C sensor for me? And if it goes outside of this valid range of data, then send Linux an interrupt. Other than that, I don't want Linux to ever know about this. I don't want it to look at it. I don't want it to do anything until it asks for it. And in that shared memory, if, let's say, we're reading temperature data, we could just write the result of our temperature data read into the DDR, and then Linux can come and read it back. And Linux never has to think about I²C. All it has to do to read the temperature is read the result from the DDR here. And we've totally offloaded all of the processing from Linux into the FPGA fabric, and we go 30 or 64-bit to 32-bit offload CPU. And what's really nice, I didn't put it on my slide. And I do have a demo of this working I can show people later. It's just really hard to make it look cool, except saying here, all of these LEDs are independently controlled by different CPUs. But what you can do, what is really fun, because you're like God, because this is an FPGA, so you can change anything, you can individually reset all of the CPUs. So I don't have to build an application for each one and then deploy it, and then it's hard-coded in an ASIC. All of those CPUs, I set them to reset from the DDR, where there's 100K of instruction, or 100 instructions that you can write in to tell it where it should jump to, or if you have a tiny application. And then you put your Zephyr application a little bit further up the DDR, the CPU starts up, it jumps to Zephyr and starts running it. And then, because this is Linux, you can run West on it. So then what's really cool is Linux on the SoC FPGA can run West, build the Zephyr apps, and then deploy them to the individual offload CPUs that are running in the FPGA fabric. And then if you're in space and you decided that your I²C sensor, all the values needed to be a little bit off, or there was some tiny bug or whatever, you can, on the fly, without having to bring the whole system down and bring it back up again, deploy new applications to all of your Zephyr offload cores. And your Linux system is never going to get bogged down with interrupts. It's never going to have to read from I²C, which is really, really nice for Linux. And your whole system gets a whole lot faster, a whole lot more stable, and it's a whole lot nicer. So I did get it in here. So Linux is Linux, and yeah, it'll run West on the fly and build and deploy all of our payloads. In this case, each of our soft CPUs can get the I²C dense data, process it, write values into shared memory, and generate an interrupt for Linux if the data is outside of range. Linux gets data by reading shared memory, which is really, really fast, and Linux only cares when there's bad data. So you can have a drone, or I think I have it written down here. Yeah. So you can also do it with PWM, for example. So each CPU can control a motor via PWM or a series of motors. And then Linux can create a series of actions. So as in change the PWM speed to this, and then after 1 second, change it to this. And it can write a whole script for every CPU to execute and then deliver to all of your motors simultaneously and completely in time. Or yeah, the other one, we came up with a few ideas. One of them was drones, is that Zephyr can control the motors and then also check for distance sensors. So you have a core that's dedicated to checking that you're not going to fly into a wall, for example. Now, there are a whole load of considerations. So, like, it is Zephyr squared. It should really be Zephyr asterisk as a title for a presentation. There are loads of things to take into account. So, DDR bandwidth is 1. So, it's really interesting. The Neo RB32 has a nice little configurable iCache on it. So, you can set up the size of cache. So, once you don't start all of your CPUs at the same time, and everyone tries to read from the same memory, you can then balance out the performance by using the cache and starting them up with a little bit of delay and sequencing between them. Timing, the speed you want to run them at, and the FPGA resources you have is a big one. The use model, how you actually want to use this, because it is somewhat specific. The layout, so whether you want dual core Zephyr CPUs, which I don't think Zephyr can do right now, if you want a new architecture, if you want to isolate all of them, and then the boot methodology and deployment of payloads. But yeah, this is what you can end up with, where you have an OS and 4 application cores, and then hanging off the bus is a whole load of custom CPUs to do whatever you want them to do. Yeah, so doing the maths, Neo RB32 uses 5,000 logic elements. There are extras on top of that for the buses and the interconnects and DDR controllers and all of that kind of stuff. So I'll say about 20,000 logic elements for 32 Neos. So 16 Neo RB32s will be 16 by 5,000 logic elements, and I said plus 12 as a random overhead. So 92,000 logic elements, and 32 will be 32 by 5 plus 20, so 180. So the 92,000 logic elements, 16 cores will fit in this 95,000 logic element device here, which comes in 11 by 11 as a package, so that's quite nice and quite small. And then the 180 will go into one of our 250 devices as well, which go from 16 by 16. So it's quite cool. It's quite nice to be able to fit so many CPUs in such a small device. Yeah, so In the SoC FPGA, you can run a dedicated Zephyr instance on an ASIC core with Linux running on the other. So remember I showed you the AMP originally, where we took one core from Linux and gave it to Zephyr on an ASIC. So we can do that. So that's traditionally known as AMP. We can do it in the FPGA. We can also do it on our PIC64. And then having an FPGA, you can take advantage of the fabric. So you can put additional CPUs capable of running Zephyr into the fabric, and they can control all your other peripherals in different parts of your system. And then in the SoC FPGA, you can have Linux running on the ASIC with Zephyr cores deployed in the fabric and dynamic payloads compiled and delivered via Linux. So you get an OS doing management and real-time workers in your CPUs. So why Zephyr? And this one is really difficult to write as someone who works for a manufacturer and not as a Zephyr developer, but I tried to sum it up. Is you could run bare metal or any RTOS you want on the soft CPUs. The Neo RB32 is not a Zephyr CPU. And I kind of asked the question earlier, is there a CPU that Zephyr is coalescing around? And that's absolutely correct. You can run anything on the CPU. But are any of them as easy to use and plug in and play as having something that out of the box comes up as a known good CPU configuration that runs Zephyr in an FPGA? Probably not. Do they have the same driver and ecosystem support? Probably not. I've tried to get bare metal drivers for sensors and then put them on a CPU or run them on a CPU that I've had in the FPGA fabric, and I've ended up with a driver for some random CPU that someone else made that took me a week to port in to find out that there was some GPIO that had a different polarity to the one in my device, and it took ages. So having an ecosystem and driver support there is huge. And the big question I have is, do people want anything other than Zephyr at this point? Is someone will want to write bare metal? They know what they're doing, so let them write bare metal. But the vast majority of people want to do what everyone else is doing, and they want to be on the train. And it's much easier when everyone does the same thing, and everyone seems to be doing Zephyr. So that's where it's very interesting for me. So I tried to power through as quick as I can to not keep us here, but if you have any questions, please let me know. Or yeah.
I'm not sure if you have mentioned it already, but one of the big advantages running Linux on such an FPGA like this, you can also change the hardware where the CPU is running, or basically the CPU in your fabric by Linux. So, for example, if you detect a hardware bug or you decide to need, for example, a watchdog in your CPU too, then you can redesign the CPU, upload it to Linux, Linux uploads it into the fabrics, and you have the new CPU there, and then you can run Zephyr on this CPU, and you basically don't have to change anything on the PCB. So I'm not sure if this is possible with this Microchip FPGAs to reprogram it.
Yes. Yeah. So we have power up reprogramming is in, so we can reboot and detect there's an update and then program ourselves, or Linux can trigger an auto update. And my description is you can email a new ASIC to your satellite and it updates itself.
What I want to say is you can basically update the whole system with Linux, and you can then do also auto updates for your Zephyr code from this Linux. And this is really nice. It's a bit complex. It brings a bit of complexity to the system, but it's also nice to see, in my opinion.
What I did to enable, let's say, I'll go back, this one. I just put the CPUs in and I set the reset vector to this DDR and then use the GPIO to control the reset.
Yeah, okay.
And then Linux just deploys the Zephyr out to the DDR and then releases the reset, and then the core boots up and runs.
Yeah, okay. This is quite simple.
Yeah, okay. I spent a week. I went from writing my own custom hardware reset controller to going, I could just do the DDR. Yeah. Cool.
Yeah. So when you talk about the kind of AMS, right, asymmetric multiprocessing, so what we see in SoC, where you have M series and A series, the connection between, or the data check changes between these two when run as Zephyr and on Linux, we see message queue or a kind of a mailbox, right? So you use an shared memory here. What is is it kind of, what is the difference? What do you see?
Okay, so I didn't want to break everyone's brains by putting too much on the block diagram. So we have an IP core, so it's either for the SoC FPGA or you could use it in this context for inter-heart communication. So that's providing a mailbox for cores to write and pass messages through. So we do have that functionality. It's just in this case, this was more just sensor data than passing instructions or anything actionable. So that was why I wanted to keep it simple more than anything else. But the IHC, the inter-heart communication or inter-core communication, there's so many acronyms. We support that. We have to support that to enable it. Mm-hmm.
Right.
Did you have a question? Or?
Yeah. So in your diagram here, you use Linux to do all the field programming.
Mm-hmm.
Is that strictly necessary, or is it just so you could use a microcontroller to program an FPGA, and therefore you wouldn't have to have a full Linux system on your PCB, for example? Would that make it much more complex, or is because I don't know, is it a tooling thing? Is it much?
I just wanted to be able to run West on it to deploy the apps.
Right.
I wanted to be able to run West on it. That's all.
I know,
but you could.
If you don't have West available because you don't have Linux, does it make it much more complex, or is it still?
You just need somewhere to get the payloads from, the Zephyr applications from, and then something to orchestrate distributing. So that could be bare metal. You could just literally pull this one up here and use one of those soft CPUs to do the coordination.
Okay.
You just need one manager. Right. But it's more, I deal mostly with the SoC FPGAs, and that's the one I had on my desk. But the Linux is not required. It's once you have somewhere you can store the binary that you're going to run, and then a way to get it and copy it. That's the main thing.
All right, thanks.
Sorry for asking more question. So the main thing is sorry for bringing up the name. Zinc has where you have shared resource and also dedicated resource. Peripherals for program logic and dedicated resource for processing system, right? So do you have something similar to here as well for the PolarFire?
Yeah. So the way I don't know if a picture of it, I can show you a bit better here. The way we construct, or the way our FPGA is done, it's quite similar. Everyone builds the same ones. I'm just trying to get back. I should have just gone out there. So, we have PolarFire SoC is the same idea. So we have our CPUs hardened on the side of the FPGA fabric, and then blocks around the outside. So the CPUs actually have, for example, a DDR controller, USB controller, or Ethernet, CAN, UART, whatever you want. And then we have PCIe on the side of our FPGA fabric, and then LinkedIn. So it's the same general idea. Yeah.
So it is kind of programmable. Is that what you mean?
Yeah, it's an FPGA.
Program or configure what peripheral needs to be configured for PL and as well as processing system. Is it?
So the processing system is all configured through software running on it, and then the programmable logic, because we're flash based. Sorry, that's the main difference. So you program our FPGAs, and then you don't need to reprogram them at boot. They retain their programming across power cycles. So that way, you don't have to constantly program the programmable logic. Once it's up, it's up, and that's it. Yeah.
Okay.
Did I answer your question, or
maybe I'll just take.
Maybe I could talk to you about it after. Yeah, that's perfect. Yeah. Cool. Okay. Anyone else got anything else? I think we're quite close to time. No? Cool. Thank you all very much.